2 videos in one day. I know, pretty crazy. Today, I will also be talking about periodic trends in the periodic table. Ta-da! So the first one that we have is electronegativity, and that is the attractive force that the nucleus of an atom exerts to attract an electron. And so the more protons that you have with the same amount of electrons, so think of that as moving across a like a row, the higher the electronegative pole. So we have the same amount of like electron shells around it, but all that we're really increasing is the number of protons. So obviously the more protons that you have with the same amount of electron, so you have to remember like nuclei are attracting electrons, and the other electrons in that atom are providing a repulsive force. So the more nuclei that we have and the same amount of electrons that we have, we're obviously going to have more electronegativity. Similarly, the more electrons that you have with around the same amount of nuclei are going to weaken the electronegative pole. So typically all these trends are going to point towards fluorine. Fluorine's the king, so everything kind of like goes up and right. So as you go to the right of the periodic table, the more atoms want to fill their valence shell and have a stronger pull, and then also the higher you go, you have kind of like less and less of electron repulsion. Next is ionization energy, and that's the force that is needed to remove an electron from the valence shell. So the more electrons that you have in the valence shell, the more likely the atom will be wanting to give it up. So that is the topic of electron shielding. So electron shielding is when you have a large number of electrons, and let's say like a normal nucleus with like 1 electron versus the same nucleus with like 10,000 electrons. The pull of the nucleus will be stronger for that one with 1 electron, because in the one with like I think I said 10,000 electrons, that one will have less of like a nuclear pull because it's being shielded by all the other electrons. All the other electrons are being pulled in by this nucleus. And so if you add 1 more electron there, it's not going to have as strong of a pull because it's already worrying about the 10,000 other electrons it has to pull. So in this sense, if we're trying to remove an electron, we would have less force needed to remove it if there's more electrons in the valence. So if there's more electron shielding or more electrons present, it'll be easier to remove the electron and we'll have less force for it. In contrast, if there's like more protons in the atom with the same amount of electron shells, then you will have more force needed to remove the electron because the proton pull is a lot stronger there. So when we compare like lithium versus fluorine, lithium and fluorine have the same amount of shells around their of the atom, but fluorine has 9 protons. Lithium only has 3. So more protons, same amount of electrons, means that you'll have a higher force to remove an electron because the pull is stronger. Also with second ionization energy, so that's the second ionization energy is the force that it takes to take away another second electron. And that's always stronger than the first ionization energy because when you have the first ionization energy, you're going from a neutral particle to a charged particle once you remove an electron. So you're going to have a cation. With second ionization energy, you're starting with that cation, and so you already have a charged particle, and now you're wanting to remove another electron. And removing electrons and moving them around from charged particles is a lot more difficult than removing them from a neutral particle. Although even with that neutral particle, as we mentioned, it can have differences in force. So again, fluorine's the king. We're going up that trend. Electron affinity is the energy that is released by an atom after it attracts an electron. So the way that I think of this is kind of like, if fluorine or the atoms in the top right of the periodic table, they really, really want electrons because they don't have that many electrons and they have a lot of protons. So they're going to have like a sigh of relief. They're going to like release energy when they attract an electron. And so it's the same trend we've seen. It's just who wants the electron more. And whoever wants the electron more, whoever needs the electron more, is going to have a higher energy release like the tension's going to be like released. That's the way I think of it. But again, fluorine's the king. Then we have Zeph, or nuclear effective charge. So we have our proton, okay, and we also have this electron shielding going on. So when we have the protons, we have to take away the force of negation that's provided by the electrons within the electron shielding, and then we get the actual nuclear effective charge. So that's like the actual pull of the nucleus when you take away the repulsion of the electron shielding. And when we talk about this, it's usually in regards to valence electrons when discussing the electrostatic attraction to the atomic nucleus. So valence electrons are the ones on the last shell, and so the I want to say pull, but that's not a very like fancy word. But basically, the pull that the valence electrons feel on the edge varies depending on how many electrons are present. So the higher electron shielding, the less pull that they're going to feel, and also the amount of protons. The more protons, obviously, the more pull they're going to feel. And that is it. So thanks for watching. We had a couple videos today, so ta-da!